Hey guys, welcome to another lesson. So today we start a new topic. So if you would ask someone that sat the HSC for extension 1 and asked them what the hardest topic or subparts of a topic is, they'll probably reel off a few topics like projectile motion, differential equation applications, maybe even vectors. But binomial theorem, identities, proving identities is probably up there. If not, it's one of the big three. I keep describing it to my classes where, in terms of difficulty, it is up there. So today I want to show you to start the framework for proving these identities. And over the next, I think, 4 lessons, I'll do just to show you the types of questions that are out there. Now, can I just say, with the onset of the, it's no longer a new syllabus. It's been new for, I guess, it's been the syllabus for about two years now. So I should really stop calling it a new syllabus. But ever since the change to the NESA syllabus for extension 1, I guess I'm a bit disappointed because as part of the syllabus descriptions, a lot of teachers have started adhering to NESA's proposed syllabus structure and putting binomial theorem and its proving identities into year 11. Now, it's disappointing because when they do that, they basically omit a lot of the harder identities that still appear in year 12. So they'll have to revisit the topic again in year 12. It makes no sense because previously in the old syllabus, binomial theorem for most schools, if not all schools, was done late in year 12. Right? What does that mean? It means that they've done calculus, they've done integration, they've done differentiation, and then they do it with the questions that include integration and differentiation. So I guess what I'm trying to say is I'm a bit disappointed that some schools now introduce this in year 11 because they leave out those questions, which I guess for these few videos, I will include the calculus stuff because you're going to see it in year 12, right? So that's a little bit spill there about my disappointment about the new syllabus and how teachers are adhering to the proposed syllabus structure. Look, so let me start the theory. We'll start with a bit of theory on this and then dive into it. So I think this video, in terms of questions, is going to be relatively short, and it sets us up at least the framework for the next few videos where it gets progressively harder. And the last video, which I don't really have a good name for it, but call it harder questions or harder applications, where a lot of the HSC questions basically are quite complicated when it comes to binomial theorem. So all right, let's start. So binomial theorem, proving identities. Now, I think it's fair to say also that when you think about when the syllabus talks about binomial theorem, there is sort of, I'd say there's 2 aspects. There's proven identities, but prior to that, the introduction of it is done where you see questions where you find coefficients or the greatest coefficient. So this part of the theory doesn't talk about that, right? It's assumed knowledge. So we're just dealing with the latter, the proving identities, which I think it's much harder, much harder. So I'll start with, everything sort of begins with Newton's formula, right? The expansion of the binomial to the power of n, a plus b to the power of n, where Newton basically says the expansion of this. Now, we have seen this with using Pascal's triangle, where Pascal's triangle is a neat way of seeing all the coefficients in terms of numbers. Replacing those coefficients with combinatoric expressions is what Newton's formula is all about. So that's like nc0, a to the power of n, no b's, c1. So as you progress along the expression, the powers of a drops by 1 and the powers of b starts increasing, plus nc 2a n minus 2b squared, right? And then so on and so forth, right? So sooner or later, there's a general term in the middle, which if I was doing the finding coefficients, I always put that in there. But for these identities, I'm just going to leave that out and go to the last. Well, maybe I'll develop the second last term. So nc n minus 1, a last a value power 1, b n minus 1, and then the finale, the final term there, ncn Bn, right? And that there is the foundation for us starting this part of the proving identities topic, right? So now that's all well and fine. It's not very useful though for most of the identities. So if you've seen as many proving identity questions as I have, you'll find that this starting block here in pink is fine. It's not the most useful, right? It's not the most useful. So what they do, right? What the questions then go on to do is basically they go, can you please let A equal to 1 and B equal to X, right? Because then you get this really neat little polynomial development where all the powers of B, so if you replace all the B's with X's, you sort of get all the X's increasing by 1 in power, looking like a polynomial, right? And if A is 1, then A essentially disappears from all our expressions because you're multiplying by 1. So you get a nice little binomial expression, binomial expansion, right, to look like. So NC0, now NC0, A's gone, right, because that's 1. So let's just shortcut that process. NC1, now A's gone, right, B to power 1, so that's X plus NC2, A's gone, X squared. So you see a little nice little polynomial development, right? Plus NC n minus 1, X minus 1, n minus 1 rather, and then NCN X power of n, right? That's a nice little, this expression becomes the starting point for, I'd like to say all, but let's not, most 99% of all questions that we'll see in this topic, right? So let me play for you the types of questions that I'm going to bucket in this topic. Now, there might be others, right? Let's put that as an other bucket, but the first one I'm going to do today is substitution, right? So basically, there's the easiest type of binomial theorem proving identities is when you just sub numbers in for X and N, right? The second type uses calculus. Like I said, most schools don't do this now in year 11. They throw it in year 12 just before they end the year 12 syllabus. We do that next week with calculus, differentiation, and integration. And then there's one more which compares coefficients, right? That's the bucket that I do. It's possibly the hardest one, right? In terms of technical understanding, it's the hardest bucket. And then there's another bucket which then applies binomial with harder concepts as well. We do that in the 4th year. So guys, I'm going to show you one classic question to start off with, and then I will show you a past paper question to sort of close it off. So starting with this green box, you know what? I'm just going to, because this is so important, I'm just going to copy this green box as a starter. Actually, let me give you the question. The question in this case actually has a starting point anyway. So consider the expansion. So most questions, they give you the expansion, or they say consider the expansion, and then they tell you which one. Now, consider the expansion. In this case, can I, for this question, I'm just going to write the combinant or express the combinatoric notation in the other format, right? So instead of writing NC0, I'm going to write it like sort of this, just to make sure we've covered both notations that you'll frequently see in questions. So this is exactly the same as prior, the green box there. All I've done is basically replace the combinatoric expression with these n guys, and I'm going to leave out the n minus 1 because it's a bit superfluous for our purpose here. Okay. So consider our experiment. That's part of the question, right? So the first and most common question, all right, show that it's a 3-parter. All right, some questions might just start in part C. Some questions only give part A. Right? So just be aware that that's the case. So that guy plus that guy plus that guy plus NCN in terms of combinatorics. Sorry, that's a bad N. Let me rewrite that. Equals to 2 pattern. Yeah. Now, classic, right? Classic part B. NC0 minus N1 plus N2 minus 1 power of N equals to 0. Yeah. and then C, let's go N0, and then it jumps to N2, N4. And this one has no last term, right? That's important, equals to the N-1. Now, these three go really well together, right? As like a sort of storyline, right? That where A and B leads you to C sort of thing, right? It's a very neat little storyline. So whenever I teach this to my students, I always ask them, right? Well, if you look at part A, right? Just look at part A. It's really important for you to identify what variable does it not have, right? Compared to the expression that you're given with, right? I mean, the variable that isn't in any of these is X. X is gone. So what have they potentially done? They've potentially subbed a number in for X. That is the most obvious solution. Now, sometimes it doesn't work. Sometimes the questions get a bit harder where even if you sub a value of X in, it doesn't give you what you want. In these three cases, it's all about substitution, right? Actually, in the first two, it's also about substitution. Number three, part C comes from A and B. Now, so you can see in this expression here, what's really important for you to identify is that everything's positive, right? So then, and all the combinatorics terms, right? N0, N1, N2, they're not, they're there, you know, unaltered. So it just looks like they've subbed in X equals to 1, right? So in this case, yeah, sub in X equals to 1. That's all they've done. Yeah, and just maybe with one eye on the next one. In the next one, then, what have they done? It alternates in signage, which means it feels like they've subbed in X equals to -1. Because when you sub in -1, anytime it is an odd power, it'll go negative, right? That makes sense. And then number 3, we'll talk about that later. But for now, let's do part A, where we go sub. You know what? What we will do is let's call this expression here number 1, right? This allows us to go sub X equals to 1 into number 1. And when that happens, right, we say therefore, and if you bear with me here, I'm going to reverse in terms of writing up my working out. I'm reverse the order. I'll do the combinatoric side first. Therefore, now always show your teacher the substitution, because otherwise you just get to the answer quite immediately. So sub 1 in plus N2 1 squared plus all the way to N 1n, right? And if I sub 1 into the 1 plus X to the power of n as well, that's how they get the 2 to the power of n, right? So at this point, it's very simple to see all the ones go away on the left, on the right becomes 2 to the power of n, and you have, so therefore n0 plus 1 2 n equals 2 to the power of n. Tick, right? You know what? I'm just going to have one eye on question C. I'm going to call this number 2, right? Just one eye on C. Now, what do I do for part B? Exactly the same, right? In fact, if you let me cheat like this on the PowerPoint pack, I'm just going to copy paste, right? Just to save you and I a bit of time. Place it right underneath each other, and I'm just gonna make subtle edits, right? I'm just gonna get rid of that, make that into -1, and literally change the ones into a negative, which means these guys alternate in value, and that will leave a bit of space in the last term as well, and that obviously changes. Give myself a tick as well. So sub in X -1 into the same expression, right? Because then what you get is you get -1 there, you get -1 there, -1 there, and 1 plus -1, right? And then what we find is that every time it's even powered, it's positive. Every time it's odd powered, it's negative, right? So then positive, minus, plus, minus, ... Now, what about n? I don't know whether n is positive, odd or even right now. So what happens? I leave this expression for the -1 to the power of n in there, right? So plus -1 to the power of n, which if you look at what I have to prove, that's why this guy has a term there, while the positive case was always going to be positive. There's nothing there, right? Yeah. And I know that on the right-hand side then, -1, sorry, 1 minus 1 is 0. And that's exactly what I want, right? And I'm going to label that as number 3. Is that okay? So all I've done for question B is do exactly the same as A, but sub in -1s and then alternate the signs. And the right-hand side 0. Yeah. All right. You can imagine that, and the training for you when you do these questions is if you look at question C, all right, how do you know that it relates to the ones above? Well, there's something to be said. Every time I say to my students that whenever you note things going up 0, 1, 2, you're going to use the original expression, right? However, whenever you note that the combinatoric terms are missing values, in this case, 1's gone. Oh, sorry, all the odd numbers are gone. Then something's happened. You're going to basically use some sort of other operation in here to cancel those out. They don't just go from the original expression, unless you're targeting certain substitutions. They don't usually go away. Now, so what happened here? And it's quite obvious, right? So if you look at question A and question B, if I added the positive and the negative terms here, they go away. So if I want the odd numbers to go away, I add, right? Part A, part B, I'm going to add them and the odds go away, and then I pretty much will get what I want. Now, alternatively, if the question was 1, every odd number, right, then I would minus the 2, and then the odds would stay and the evens would go. Is that okay? So a very classic question is when they skip a combinatoric term, which basically means that, like, most of the times you've done something to the part A and part B, right? So in this case, we called it number 2 and 3. So all we need to do for part C is state, I want to add 2 and 3. These are like simultaneous equations, right? I'm just going to add 2 and 3. So if I stack these two together, right, you can sort of see, right, visually, this guy adds with this guy. There's 2 of them. This guy cancels out. This guy adds with this guy, 2 of them. Every odd one cancels out, but every even one, there's 2 of them. So what I'm going to do is basically go, there's 2 factorized of all the evens. And because I don't know what value n is, right, I'm just going to go ... and just leave it as a repeat, a sort of recurring expression that goes to infinity or to whatever n value is, right? There is no limit. There is no value, right, needed. Now, and on the other side, I'm adding 2 to the power of n with 0. So then I can go, that's 2n. Well, technically, I can go plus 0 if I really want to show my teacher I'm working, right? And then we're almost there because the question basically says, I want this, which means I need to divide this guy over, and that's how they got the 2 to the power of n minus 1, right? When you divide the 2 over, 2 to the power of n divided by 2 is 2 to the power of n minus 1. Yeah? Plus ... equals to 2 to the power of n on 2, which equals to 2 to the power of n minus 1. Tick. Yeah? Is that okay? So how do you know that this is a substitution question? Well, the question itself is missing letters. So they must have done something, right? Sometimes they might even replace a number with n as well, right? Sub n as a number, as you'll see in the next past paper question, right? So hope that's okay to start off the process as a proving identities question, right? Let's do another one. All right, let's do one more question from Sydney Grammar back in 2006, where 3 marks, 3 in a paper, very classic. Use binomial theorem to find a simplified expression for that. So I need to basically simplify that with the expansion. Now, interestingly, x is positive there, negative there, right? Once again, ring that bell, right? Because look at the alternate, look at the skipping here, right? And hence evaluate this. Yeah. So a couple of things to note. Part 1, they're saying use binomial theorem to find a simplified. So they want me to, when they say that, they want me to sub in the expansion for both. And because one x is positive, one x is negative, they're going to cancel out. Things are going to cancel out. Or the odd numbers are going to cancel out. I know that. Or I'm adding. Odd numbers canceling out, really good for part 2. Look at part 2. The combinatoric terms, no odd numbers downstairs. But what's really important, remember I always say, well, I always tell you that I say to my students, what's missing in 2? There's no x's. So they've subbed in a number for x. What else? There's no n's. They've subbed in a number for n as well, right? So keep that in mind. All right. Let's do this. What I'm going to do for illustration purposes, right? I'll just do this in isolation. Oh, sorry, this is 10n, right? Not that it makes a difference. Right? The only difference actually that it makes is that I start with 10n 0 plus 10n 1 plus 10n 2 plus 10n, oh, I forgot the x, didn't I? X squared plus 10n, 10n, 10n. Yeah. Now, so then by the same token, if they wanted me to add these, right? You know what? Let's be brave. Let's just put them in the same line. Yeah. So if I added this to 1 minus xn minus x to the power of 10n, right? I'm then adding this to the same expression. Yeah, maybe I'll stack it up on top of each other. So it sort of looks like 10n 0 plus, oh, sorry, when it's a minus there, right? It's almost like this is a minus, and so automatically I can start alternating the odd numbers already, right? So okay, so that's like subbing in that plus 10n 2 x squared, then minus plus blah 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 in the middle, 10n times. Now that's negative. So now 10, the reason why I put 10n in is because I know 10n is going to be an even number, right? So then if that's an even number, the last term is going to be positive, right? Good. Now, so what you'll see here is, and maybe for illustrative purposes, I'm gonna put in an extra term, right? I'll put in the cube term just to have another odd number in there so you can visualize it, right? So plus 10n 3 x 3 plus, yeah, while here it's minus 10n 3 x 3 plus. Now, what's important here is, you know, in the previous question, when it was just n, I didn't know whether n was even or odd. So therefore, I didn't know whether the last term was positive or negative when I subbed in negative. 10 times n is definitely an odd number because 10 is even. Any even number times an integer would be an even number, right? So the last number is even. Now, the importance there is when I add this, the odd numbers go away and all the evens double up, right? Just like before. So I know then this expression will be 2 times all the evens, which includes the last term. Now, unlike last term also, at this point, they haven't subbed in anything for x yet, yeah? So I'm just gonna put in my terms with my x's in there, 10n there, and leave that. Yeah, that's sufficient. That's my answer, yeah? Now, if technically speaking though, 10, just looking at with one eye on where I want, technically speaking, any combinatoric to the C0 would be 1, so I can actually replace that with a value of 1 if I really wanted to, right? Let's do it because it's going to be a 1 later, right? So 1 there. Actually, I'll put in blue just to identify with this 1 over here. All right. Cool. So part 2, what have they done? Right? What have they want you to evaluate this. So if you can imagine, right? What have I proved? So in part 1, let me just write the expression because the expression then allows us to visualize what I'm going to do next. In part 2, what have they done? Part 2 looks like it's an expression that deals only with this, right? So what we're saying is from 1, if I just made this blue bit the subject, I'm going to divide the 2 over. I go 1 plus 10n 2 x squared plus all the way the 10n, 10n, x 10n, x plus n should be all over 2, right? The 2 comes over because there's a 2 there and I divided it over, huh? All right. So guys, what have they done? Hopefully it's not too bad, right? Hopefully it's not too bad that you can see. It looks like, firstly, x is gone, right? X goes away, so then it looks like they've subbed in x equals to 1. Yeah, it's all positive as well, so x equals 1. Also, the top combinatoric, right? Top number, right? All the n's are gone. But what have they replaced it with? 30, right? So they want this 10n to be 30, so they basically said let n be 3 as well. That should give me everything, because if all the x's go away, and if n is 3, then the combinatorics line up. So what you should say is sub in, or maybe I'll call this number 1 now, and I'll do it in pink, sub x equals to 1 and n equals to 3 into 1, all right? And that should give me it. That should give me it. So therefore, I got 1 plus, let's do it in 2 steps where I show my working. So times 3 power 2, 30, right? Times 1 squared plus, now I'll put in the 4 n value as well, because the question has it, that's all. So I'll put in the 4th one. I'll put an extra term here. Because right now it's still captured in my dot, but let's actually show that's a 4 plus 10 times 3, 10 times 3, 1 to the power of 10 times 3. And more importantly, on the right-hand side, what did I sub in? 1 plus 1, 10 times 3, plus 1 minus 1, 10 times 3, all over 2. Can I fit it? Yes, I can. Therefore, 1 plus 32 plus, let me have a quick glance at what I need to prove. 32, excellent. 34 plus dot, dot, dot. 30, I believe would be the last term. Now, sometimes they get tricky because that value there is also 1. So technically I don't need it there. So let me just glance up. 30 is there. Sometimes they replace 30 with the expression of 1, right? Just to throw you off. Now on this side, what happens? So I got 1 minus 1, that's gone. That's 2 to the power of 30 on 2. So 2 to the power of 29. Just like in the last question, it was 2 to the power of n minus 1. Same thing here, guys. That's how you do it. Yeah. So in this question, it was a clear question to me of substitution because the x's are gone and it's predictable, very similar to the last question because all the odd combinatoric terms are gone, right? So then it looks like I've done, and the first part actually told me that I'm adding the positive with negative, which is essentially part A and part B in the last question. Guys, that's the framework for doing this. We always start with the 1 plus x to the power of n expression, in this case 10 to the power of n, same thing. And that's the foundation for us to then derive our values. The next lesson I want to do relates to calculus type questions. The third one is comparing coefficients, quite hard. And then the fourth one, yeah, crazier questions from the HSC and just harder questions in general. Guys, hopefully that was good. If you like that video, give me a like, tell your friends. Yeah, and I'll see you in the next video.